Lawton is going to give me the last talk of the morning session. He's discussing the BETTI moduli space experiments and visualization.
All right. Well, thank you very much, and it's a absolutely huge honor to be here today. And I suppose maybe at the last talk someone will say this, but I wanted to thank the organizers for just doing an amazing job. Oh, louder, yeah, like that. Okay, so I want to thank the organizers for doing a fantastic job. Maybe we can just give them an applause now, right? I mean, and also, just again, it's a great honor to be here speaking today. So that's Bill at ICM in 2010. He gave an invited address there. I think sometimes I feel like I'm a Bill Goldman groupie. Just following him around the world like your favorite band. And now and again you catch your favorite guitarist doing their solo or something, and you're just like, wow, that was amazing. I'm glad I was here for that live performance. And that was sort of like how I felt in Hyderabad. Bill just gave a just amazing talk on homogeneous structures on manifolds, and anyway, okay. So but that's 2010. So I met Bill much earlier than that, in the late 90s, when I was an undergrad.
Go back.
In the experimental geometry lab, that was where I had my experience with Bill. I did have hair. That is how Scott remembers me. The picture's a little bit fuzzy.
You're holding the other part, I remember.
Yeah, well, there's other pictures like from that. I was looking for some, but none of them I'm willing to put on a screen that's being recorded. Right. So that was the late 90s, and so I first met Bill. He gave a fantastic course in differential geometry that helped me fall in love with topology, because it turned into a topology course. But then, so I decided I wanted to go to grad school at Maryland to work with Bill. And so I started, and I went to Bill, and I said, I loved, working with you at EGL and the courses I've taken with you. I'd like to work with you. And Bill was real excited, and he said, great, you should go work with John Milson. So that went well. John and I, talked about polygon spaces, and it was fantastic. And shortly thereafter, John fired me. I don't show up to places on time, and I didn't quite work with John. No, but John's great. I love John. Anyway, but yeah, so I went to Bill, and I was crying and deeply upset, and what am I going to do? Bill, will you please take me back? And Bill was like, oh shit. This is going to be one of those 11-year plan things, isn't it? PhD student you can't get rid of. So Bill had a bright idea. He said, okay, fine. All you have to do is just solve one task. Do one task for me. You have to find a mistake in one of my published papers. And in no time at all, I was receiving the quality mentorship that we all have come to expect from Bill. But incidentally, that is actually Bill's handwriting from around 2003. So around the time I actually was able to dig up some old notes. I'm a math hoarder, I admit it, and so anyway, pretend M is closed. Right, teaching me the Fox calculus, which eventually led to a transactions article about the Poisson structure on the SL3 character varieties. Anyway, okay. So I worked on character varieties. That's what the upshot was when Bill and I started working together again. And so we all know what a character variety is. Sometimes they're called the BETTI moduli space because there's a relationship to singular cohomology, and algebraic geometers like to refer to the singular cohomology. Singular cohomology is the BETTI cohomology. So anyway, so real quick, to make a character variety, you need a finely generated group, gamma. So there's words and letters. And I'm going to just, the second ingredient, have a reductive, real reductive group. So think of these guys, if you'd like. And so, and then the evaluation map. Embeds the set of homomorphisms into the product of Lie groups. So it's naturally an analytic subvariety. So there's a nice topology there. And then you have a nice action by conjugation. And so because Hom is now equipped with a topology, we can consider the subset or subspace of points that have close orbits with respect to this action. And I often just call this the G character variety. In this context, there's no characters, and it's not a variety. So maybe it shouldn't be called a G character variety at this point. But anyway, but by getting rid of the open orbits, you turn something that's like T0 into T1. But it turns out, by a result of Richardson and Slowey from around 1990, that since G is real reductive, you actually get its T2, it's Hausdorff, and in some, with respect to some setting, it has all of its limit points, so it's kind of nice. And if G is complex reductive, then you can say more. You can show that you can impose the structure of an affine algebraic variety on it, affine algebraic set. Okay, so there's the character variety. So here's some examples. So start with the simplest ones. So there's the gamma is just a free group of rank 1. So that's L2R. You have something that looks like this. These are the elements that are diagonalizable over R, and then these are corresponding to like SO2 essentially. So this actually example is kind of nice because it shows a number of things, even though it's super simple. It shows that there's a difference between the R points of the character variety and the character variety of the R points. And there's also also you can't distinguish points on here because it's SO2 by traces. So this is like your first indicator that you need other invariants other than the traces, like the Pfaffian. And here's another example set of a compact group here. And this is the exponential of the Weil alcove. Those who've studied Bill's book on complex hyperbolic geometry have seen this picture before. Okay, so there's just two picture examples. I'm not really going to explain any. I'm just going to show some pictures. This is like a slideshow, pictures. So that was one generator groups. So there's a free group of rank 2, and SU2. This is a solid ball. So there's another example. It's parameterized by the trace of the first generator, trace of the second one, and the trace of the product. Come back to that in a little bit. In fact, I went ahead and printed this one. So I like to carry moduli spaces around with me. So I don't know if people want to pass them around or something. You can get a feel for the shape of the thing. Here's yet another example. It's still the same gamma, still a free group of rank 2, but now I'm going in SL2C, and then in that case, there's the Fricka vote theorem, which I'll come back to later, give a quick proof of that. But it's all of C3. It's off of affine 3 space. So if you look at the R points, then it's this R3, and then if you think of the free group of rank 2 as a fundamental group of a one-hole torus. and you fix the boundary trace to be 2, then you get the thing that's being passed around with 4 little wings attached. So here's a 3-manifold example. So a torus link, in particular here, with this presentation. So this is a combinatorial diagram. Each of the straight lines just correspond to this affine lines, and then each little circle corresponds to a parabola. And there's lots of components, and then there's the diagram here tells you about how the components intersect. So I mean, this is just an example of 42 and 30. The paper being referenced here tells you how to do this for any 2 numbers there. So another example, you go with the Whitehead link. So you have a presentation here, and using a sort of algorithm that I know. So for SL2, you give me, we have a program actually written by JP that you give me a presentation for gamma, then I'll give you a presentation for the character variety. It's like an input-output thing. I only can do that for SL2. But anyway, so you can do this for the Whitehead link, and there's just a picture of its R points. So these things are very concrete.
You get the A polynomial for that too?
Yeah, I mean, I guess. I mean, so so you can use the A polynomial to describe the. Yeah, but I mean, there's different ways to. But the algorithm gives you a set of generators for the ideal that cuts it out, not scheme theoretically, but set theoretically, So I mean, there's lots of different ways to describe that ideal. I don't think that you necessarily can pinpoint which would be the, what would correspond necessarily to the A polynomial and what wouldn't. But in principle, I think you could get some information. I don't know for sure exactly. But here's another example. This is the last few examples were in terms of three generator groups. I mean, sorry, 2 generator groups and 1 generator group. This is a 3 generator group, so free abelian group of rank 3 in SU2. And this thing very much wants to be a 3-sphere. And so if you sliced up a 3-sphere, horizontally going from bottom to top, you get a bunch of balls. But this thing has some singularities. And so what happens is when you go from the bottom to the top, you don't get 3 balls, but you get these sort of twisted things. I went ahead and printed that one too, so I don't know if anyone wants to see a slice of an orbifold. That corresponds to a character variety. I don't know if you guys can start with Bill here. And you can describe the singular locus very explicitly here, and also the local, the homeomorphism type of neighborhoods around the singularities. So they're cones over projective space in this case. Okay, so about cubics, well, so if we go to another, so instead of having a free abelian group of rank 3, we have just a free group of rank 3. Turns out that this guy is a hypersurface in C7, and it's homotopic to a 6-sphere. That's an honest 6-sphere there. I mean, topologically, it has, in the trace coordinates, it has singularities, but but topologically, it's a 6-sphere. One way to so it turns out you can get a lot of cubic hypersurfaces this way. So if you think of the free group of rank 3 as the fundamental group of 4-hold sphere, so you have 7 coordinates here. The 4 boundaries correspond, it turns out, dead on to like 4 of those coordinates. So you reduce it down to 3 coordinates, and there's one relation because it's a hypersurface. So it turns out when you specialize those 4 coordinates down, you get a bunch of cubic hypersurfaces, and you pretty much, in those terms, get all of them. This was, within a certain family, so a theorem of Bill's and Toledo. And if you And if you look at the R points in the non-singular case, it turns out that there's exactly 6 things that can happen. So this is a theorem. One of those things is see if I can get these out here, starting from the bottom. Oops. Here, I can just dump them out here. It's a lot of pieces. Right. One of them is is topologically a 4-hole sphere. There's one of them. Yeah. And then there's another one that is a 3-punctured torus and a disk. So there's one of them. Yeah. And then another one is a 3-punctured sphere and a disk. So here's that one. Okay. And then the next one is an annulus and 2 disks, right? So here's a annulus. Maybe. Oops, is that one going to stand? Yeah, okay. And 2 disks. All right, that's what it looks like. Okay, and then another one is just 4 disjoint disks. Right, so you can just put those around here. This is what they look like, those, like that. And then the very last one is 4 disks. 6th one is 4 disks and a sphere. The sphere came out really tiny, though. But it's pretty much the bigger one I passed around. Yeah.
But in all these cases, you pick some coordinate system.
Yeah. It turns into traces. Yeah. That's actually the theme here. Yeah. So right. So that's happy birthday. I 3D printed a theorem for you. It's your theorem. So that's the theorem. There's only 6 things that can happen, and there they are. So right, yeah, and then so the Fricka-Vogt theorem is another example. This is the one that I mentioned earlier. So if you have SL2 and a free group of rank 2, it turns out it's affine space, and I mean, using sort of elementary ideas, just linear algebra, prove this takes about a page or something. But I mean, but here's a really short proof. Using the Caylor-Hamilton theorem and a little bit of wordplay, you can show that the coordinate ring of this has to be just generated by trace of x, trace of y, and trace of z, x, y, and that's it. But on the other hand, it's an irreducible variety of dimension 3. That's it. There can't be a relation otherwise, because you have a coordinate ring generated by 3 things. If there was a relation, because it's irreducible, there'd be a dimension drop. Okay. So anyway, we were talking about me being a PhD student. So that's what character varieties are. There's a bunch of examples. And so Bill suggested that I work on the 3x3 case of this theorem. So replacing 2x2 matrices by 3x3 matrices. Yeah, and he said, I don't think you can solve the problem. That's what he said. And so I said, I'm going to do it. So in 2006, I did, and it turns out it's very similar to the free group of rank 3 with SL2. It's a singular branch double cover, and you can write down exactly what everything is here, and these are terms of traces, and this is anyway. So the theme here is all those examples and the 3D prints and everything comes down to having explicit coordinates, and having explicit coordinates allows you to do experiments and to understand examples and look for patterns and build your intuition. So I don't know, in the what is the dichotomy frog and bird? I'm a super frog. I am definitely a froggy frog. I love doing computations and turning things into like video games and virtual reality and anything you can imagine like that. It just makes me happy. And I learned all that from Bill. It's his fault. Right. So an interesting little side note: if you look at the transpose map on representations, that actually is where the switches the the two inverse images off the branch locus. So that's how the double cover part is arises. Okay, right. So so from that description, and again the explicit coordinates, Florentino and I later were able to show that this thing here is actually an honest 8-sphere, again in C0 8-sphere. I mean, there's singularities, in the trace coordinates, but I mean, as a continuous function, it's a topological manifold. It's an honest 8-sphere, and having and understanding this like involution here and the explicit coordinates here, we were able to cut this space up here into lots of little pieces and glue it all back together and figure out what it was homeomorphic to. Oh, in the free group case? No, I don't. No. In the free group case, there's no. I mean, but there can be lots of, as a scheme, there can be lots of nilpotents away from the free group case. But in the free group case, there's no nilpotents. Yeah, I mean, things started off smooth because it's just a product of Lie groups. So in the GIT quotient, you're not going to inherit any nilpotents because the invariant ring's a subring. Okay, and again, this is homotopic. So the GIT quotient here in the strong topology, not the Zariski topology, is homotopic to this guy, and this guy is an 8-sphere. Okay. I think these examples are really helpful. I mean, especially in the free group case. I mean, I've talked to so many mathematicians who say, aren't all these character varieties, especially free groups, contractible? And the answer is definitely not. I mean, there's. Right. Yeah. But there's topology there. And in fact, this theorem generalizes, and the examples most of the examples I just shared with you, more or less, at least are part of a proof of a classification theorem. So if you let G be SL or GL, and let K be UN or SU, so a maximal compact here and a maximal compact here, then you could ask the question. I mean, this is a manifold. I mean, there's topologically, right? And you can ask the question, what other character varieties for free groups with these groups arise, have the structure of a manifold? And it turns out the theorem is, for the complex case, it's if and only if you're in the 2-2 case, and that's the Fricke-Vogt theorem. Okay, and for the compact case, it's if and only if you're in the 2-2 case, that was the closed ball. And then the 2-3 case, that was the, let's see, so R is 2, right, that's the 8-sphere. In the 3-2 case, that's the 6-sphere. And this is when R and N are both greater than or equal to 2. I mean, if R is 1, then it's a different story. And so to prove this, you use those examples that handle the one direction, and then the other direction requires an analysis of the singular locus. And then you have to also take the top stratum in the singular locus and then actually construct, neighborhoods, the final local model, and then determine the homeomorphism type of the neighborhoods, the model neighborhoods around singularities. And the upshot is you show that they're not homeomorphic to balls. Yeah. Okay. Anyway, so these are things you can do with explicit coordinates and description and examples. So of the what? The neighborhoods?
No, of the character varieties, these character varieties for free groups.
All of them? No. No.
So if to generate free group.
Yeah, no, I don't know. Yeah, not in general. I mean, even for SL4, I mean, we know it's not a complete intersection. We know when we get a complete intersection, we know we know they're Gorenstein, at least over C always. We know when they're factorial. We know that an arbitrary characteristic, but there's lots of we don't know. So we know we have a good sense of the commutative algebra picture, but the homotopy type we don't know. But we do know some of the homotopy groups, and that's actually where I'm leading to. So the main idea that I use to do all these examples and and proved a lot of these theorems, was trying to make a relationship between character varieties and non-commutative algebra. So just want to point to this as a general feature, something I've been taking advantage of for many years. So if you, the coordinate ring for the SLN case, and that's again a free group of rank R, is just a polynomial ring in R times n squared variables, and then you quotient by the R irreducible polynomials, the determinant -1. That's just on the level of Hom, nothing fancy. And then we just cluster each group of these as a matrix. You get something called generic matrices. And this is very related to a classical invariant theory problem. If you just look at the conjugation invariance of just tuples of arbitrary matrices, no determinant condition. This was studied by Procesi and others before him. There's a whole interesting history there that Formanek has written about. It's worth reading if you're interested in the invariant theory. I think Formanek says that Procesi wasn't the first one to notice that this guy was generated by traces, but maybe he was one of the first people to really recognize how important it was in polynomial identity theory and make it prominent. What's this?
The script N.
This? Y? I think it's a Y. I think.
This is chi, right?
No, it's not. This is frac X. This is frac Y. They're different things. Yeah.
What was frac Y?
Frac Y is this.
Okay, just denoting that. Okay.
Yeah, this is just, I should have like a little colon here. I'm just defining that symbol to be so what is frac Y? I mean, I could define frac Y straight up. I mean, it's yeah, but so frac Y is just the yeah, it's just SL and C. Okay, where this is the action of conjugation in each factor. Okay, so I'm not assuming the difference between the two is here you have arbitrary matrices, in the other case you have determinant 1 matrices. Okay, so the point is that there's a relationship though between this guy, and this guy here. Yeah, and that's pretty much just that you can commute taking invariance with quotienting by the ideal. Okay, that's the main idea. So the upshot is that if you look at the non-commutative ring of these guys, this is very much related to polynomial, the free associative algebra on just n symbols, non-commutative algebra on n symbols, which is the province of polynomial identity theory. So if you look at that algebra here, you get a lot of structure, not of non-commutative in a non-commutative ring theoretic setting. And if you take the trace of that, you get this guy, and then you quotient by delta, and you get this guy, and then from the coordinate ring here, you can get things about that. And so that interplay gives you gives you a lot of mileage. Okay, so it may be even surprising that you get so much mileage out of it. But pretty much all of the coordinates that were used to describe the character varieties before came about from that picture. Okay, so that was working with Bill as a graduate student. So then after that, I said, Bill, I need a job. Can you help me? I need to be employed. And he said, I know this great guy in Portugal, Carlos Florentino, and they're looking for postdocs. I think you guys would get along really well. I never met the guy. I didn't know anything about it, but at this point, I just said sure. He was totally right. Carlos and I get along famously. We really complement each other very, very well mathematically. And he's also a good friend. So I went to go live there for a while, and we proved some theorems. And there's the first one. The first one. This is actually a combination of theorems, but anyway. But the first part of it was for free groups in 2009, at my second postdoc. Anyway. So the theorem says that let G be a real reductive algebraic group, and K a choice of maximal compact. And then gamma is either a free non-abelian group or an abelian group. finally generated. But in the abelian case, we do allow torsion. And so then the statement is that this moduli space strongly deformation retracts to this one. And that was the, and I already indicated that in a couple examples where, you know, the free group of rank 3 case, or free group of rank 3 case into SL2, I said was, had the topology of a 6-sphere. Well, that we know that because there's a deformation retract to the SU2 case, and that is known to be a 6-sphere, for instance. The other example was the ball that was 3D printed around, and I mean that's a sort of a trivial example, but that's a solid ball in R3, and so the complex version of that is C3, and so they're both contractible. So their deformation retracts to each other, but that's sort of a trivial example. The other ones are not trivial. Okay, so anyway, so once you have this theorem, you naturally ask, since G deformation retracts to K, maybe, you know, this is just a general feature. Why not? But you can find counterexamples in the work of Atiyah, Bott, and Hitchin. And then later, after this, Carlos and Indranil Biswas, using Hicks theory, showed that, in fact, it's not just that it's not a general feature. In fact, it never happens, ever. And they did this by using the non-abelian Hodge theorem and identifying this guy with the modular space of Higgs bundles, and then reducing that to the nilpotent cone, and then there identifying a cohomology, a BETTI number essentially, in this setting that was different than there. And then they did it for every single genus. And G was maybe not arbitrarily reductive here, but it was complex semi-simple, I think was the setting. Yeah. But it was very, very, very general result. But that's for closed surfaces. So there are lots of Caylor manifolds that are abelian, and so this does in fact relate to some Higgs settings, right? So if you have the even rank, free abelian group, then there is a corresponding Higgs moduli space there, and then in that case, the boundary divisors which prevent this from happening in the closed surface case are not an obstruction. So I guess I'm just speaking to the people who know Higgs stuff now, but basically this guy here in the Higgs setting should be thought of as the holomorphic vector bundles, and then if you, morally it's a little bit of a lie, but if you take a tangent vector to the holomorphic vector bundle, that's essentially the Higgs field. And if that was all there was there, then you would have this deformation retraction because the cotangent bundle deformation retracts. But there's more to it than that. There are things that you have to add at infinity that prevent that from happening. Okay, anyway, enough about Higgs stuff. I didn't bring any 3D prints of Higgs, so I don't want to talk too much about it. Right, so here's a sketch of the proof. So the abelian case and the free group case really are different. The proofs are completely different. What works in the free abelian case, or the abelian case doesn't work in the free group case, and vice versa. So in the free group case, the main idea is use Kempf-Ness theory and polar decomposition. So up here, you just note that the Hom space is just a product of G's, and the usual polar decomposition, it does in fact define a K equivariant deformation retraction in each factor. Okay, so there's nothing fancy there. And so you directly get a deformation retraction there just from using the polar decomposition. Mod K, not mod G, definitely not mod G. Okay, and then you have to show that you can embed this guy well, this guy's naturally there, it's just the identity. But this guy's a little bit subtle, I mean, because this is a GIT quotient, and this is, you know, a regular orbit space, and it's not terribly complicated, but anyway, but there's something to do. So you show that's an injects, and then you have to define a section to this projection here, and that comes from Kempf-Ness theory. So Kempf-Ness theory allows you to so each one of the points here corresponds to a union of orbits, and then in that union you want to pick one of the suborbits, and then within one of the suborbits you want to come up with a way to identify a K orbit. Okay, and Kemp's theory allows you to do that, and allows you to do it in a continuous way in particular. And so you get a section here, and then the trick is to also show that that section corresponds with the natural occlusion here. It doesn't necessarily have to. The image of the section could be perturbed slightly. But you do all that, and then you show that this diagram commutes, and then going up, over, down is your deformation retraction. So that's the quick version. Okay, and then in the Abelian case, you just totally do something different. And why do you do something different? Well, the reason is because it's not just that we don't know how to come up with a deformation retraction that preserves commutivity, because we're in the Abelian case. You can prove there is no deformation retraction that preserves commutivity all the way down, factor-wise. So the idea is that is not going to work. There is no way to do it. So the result of Soto, he showed that you can't do it. So you got to do something different. And so what do? You cheat. That's how you do it. So this notation's horrible, but I like it, but it's still horrible. This does not make any sense because there is no, this is not a group. This is just a set of semi-simple elements in G, but because you're dealing with homomorphisms from a Abelian group, it's finally generated. There's a certain number of generators, so you can think of them as tuples. Okay, and you can say, like, look at the tuples, which correspond to homomorphisms, the tuples that have their output at the generators semi-simple. Okay? And then it's a conjugation invariant subset, and so you can look at the quotient of that. Okay? And then the trick is to note that this as a space is homeomorphic to the set of the GIT quotient here. Okay? And that's exactly because it's you're dealing with an Abelian group. So if you try to do this with a free group, it's just not going to work. If you conjugate a bunch of things, if you look at a free group that has semi-simple elements in each factor, up to conjugation, you're not going to necessarily. What do I want to say here? So I think I'm saying it backwards. If you, right, that's right. So what's actually going on here? You want to identify this, yeah, that's right, that's what's going on. You want to identify this with the set of closed orbits, the points that have closed orbits. So if you have, in each factor, if you have something that's semi-simple, it doesn't necessarily correspond to the things that have closed orbits. That's what goes wrong in the free group case. And so, but because you're in the Abelian case, that if you have a closed orbit, if and only if each factor is closed. It's closed. The orbit of each factor is closed, but that definitely doesn't happen in the free group case. So this method won't work there, and the other method won't work here. Okay, and then in the compact version, what you do, the thing you're deformation retracting down to, again, this is not a group, but this just says that you're looking at the G conjugates of things in K. Okay. And again, if you have something that has k valued in each factor, and then you do a G conjugate of each one, and the G conjugates are different, up to G conjugation globally, simultaneously conjugating in G, you can't necessarily put it in K. But because it's Abelian, you can. And that's what makes this work. So basically, you have a situation where you have something like this. And this is why I like the notation, even though it's bad. Corresponds to yeah, you can do this or something like this. Maybe I'll put this in quotes. Okay, G maybe, or maybe I'll put K here. Okay, so just that. But the point is, you have potentially different G conjugates here, and maybe sorry, I can fix this. Yeah, right. I think that's better now. Yes, now we're good. And then this corresponds to there. Okay. Okay. So if you have different G conjugates in each factor, then there is a G that will simultaneously put them all in K. And that's only because we're dealing with commuting matrices. So anyway, once you do this, then you just show that this guy, G equivariantly deformation retracts to this. And the main idea there is in this setting, because you're dealing with semi-simple elements, you can diagonalize and then you can just contract the magnitude of the eigenvalues. Basically, that's how it works. Okay. So once you have this deformation retraction, there's all kinds of nice corollaries. So Tom Baird, that's not available to you using geometric invariant theory. So Tom Baird, in his thesis, computed using equivariant cohomology, computed the Poincare polynomial of this guy here. And it's just a nice formula here. But using our deformation retraction theorem, we immediately get the Poincare polynomial and the strong topology for the GIT quotient there, which is a nice thing. But you can do more. You can also get GL by nipping off a torus. And you can also get SL3 because here by relating SL3 to SO and SO to SU2. There's a little bit more to that. There's a question of Z mod 2, and you have to sort of trace through the diagrams in Tom's thesis to make sure the Z mod 2 is acting trivially in equivariant cohomology. But anyway, you can do it. And you can also get the U22. You get O3C. Oh, sorry. Yeah. Anyway, so there's all kinds of nice corollaries. So lots of Poincare polynomials you can get for free. Okay, so this is. What time do I finish? 12:30?
Yeah.
Yeah. Okay. Right. So this was my postdoc and consequences of it. So after I finished up my postdocs, I again was inspired by Bill, and with my first tenure track job in Texas, I started a geometry lab because of my time, under Bill's tutelage. I really felt that geometry labs should be franchised. I just thought they were a fantastic idea. So it's right when I got to Texas, I started to make moves to do that, to create my own geometry lab in 2009. It was called the University of Texas Pan American then, but the name has since changed. So it's now called the University of Texas Rio Grande Valley. So both of the labs, both my current lab and my old lab, my current lab and my old lab had three main parts. One's experimental research involving undergraduates, graduate students, and faculty. The second part is visualization, virtual reality, 3D printing, movies, and other such things. And then the third part is outreach in local schools and libraries and maybe some museums now and again. And then after 5 years in Texas, I moved to GMU, and then I started my second lab, the Mason Experimental Geometry Lab. So these are just a few pictures. This is me teaching high school students about complex numbers using dance. This is me teaching elementary school kids about non-Euclidean geometry with balloons. This is a recent creation of one of our students in Virginia. We're calling this a Moy torus. It's an example of a new way to, as far as I know, it's new to create a flat torus in 3D. So you take the idea of corrugations, but Stephanie Moy, who was a student doing this, she's this absolutely amazing young woman. I guess she started college when she was like 10 or something like this. I had to spend my time just trying to keep up with her. But she's graduating next year in high school and undergraduate and a master's degree all in the same month. So she was looking for something to do, and I said, well, it'd be really cool. I want to figure out how to embed a hyperbolic genus 2 surface in 3D. I don't think anyone's seen that. And so, but to warm up, let's try to understand what these guys did in the Hevia project to do flat tori in 3D. And so she didn't really want to read their work, so she was just like, I'm just going to do it. And so, she did. But she'd use just elementary sine waves instead of corrugations. And then I don't know, I just been trying to keep up with her just to figure out what she's doing. But it always seems to work. And now she has some NAS spheres too that she's done. And she has some nice movies that she made 3D movies and lots of 3D prints and things like this. And she's presently working on the hyperbolic version, at least doing experiments and trying to get something to work. Yeah, she won the AMS first prize at the Intel Science Fair just very recently for her work. Really proud of her. Anyway, so then this is a virtual reality thing we call the throw-up simulator. It's a demonstration of the null homotopy. I think it's, what is it, like that or something in SO3. So Dan Romrus has a nice little paper where it just was accepted for publication actually, where he shows essentially that as you go through that null homotopy, like in your visual landscape, you actually see every single point in the two-sphere. So we created a virtual reality experience where you will put on the goggles and your head is at a certain point in the homotopy, and then you just use a joystick and you just go through the null homotopy. And so since you're seeing every single possible direction, you feel very dizzy. So anyway, it's a fun thing, and I think we're trying to figure out how to publish it with this paper because Springer wants us to, but we don't know how to do it. But we're working on it. This is just an example of a little picture depicting some of the experimental research we're doing right now. We're looking at the mapping class group action on finite field points of certain character varieties. And again, to do these computations and we're looking at the asymptotic growth rate as the finite fields increase in order, and we're trying to identify certain properties like maybe pseudo-anostos or something like this from the asymptotic growth rate. We're trying to just identify properties. We don't really know even what the right questions are, but it's fun. And to have but again, to do these experiments, we need explicit coordinates and be able to do computations. Okay, anyway, so that's just a little bit about geometry labs and how Bill inspired me to do these things. Another example from the work that came out of the experimental geometry lab is the work with Sam Cavazos. He was an undergrad student of mine in Texas, and he was very bored when he was taking calculus, but he was very bright. And so I gave him some linear algebra problems over finite fields to work on. And the next thing I know, we're calculating the E polynomial for these character varieties. So basically, the E polynomial, you take up your usual cohomology and you break it up into P and Q pieces, corresponding to this is a result of Deligne, that corresponding to two filtrations, an increasing filtration and a decreasing filtration, a weight filtration and a Hodge filtration, and then you get this thing. It's like the Poincare polynomial, but it's called the mixed Hodge polynomial. And instead of just being correspond to one power of t, it has three variables, x, y, and t. Okay, so you have a p power, a q power, and a t power, where t corresponds to which cohomology group you're dealing with, and p and q are the pieces that you broke it up into. So if you specialize this mixed Hodge polynomial in one direction, you get the Poincare polynomial. You specialize it in a different direction, you get the E polynomial. And there's a theorem of Nick Katz which says that if you happen to have a variety that's, if you look at the number of points over finite fields, if the counting function, you input finite field and outputs the number of points, if that function is a polynomial function in the order of the finite field, then the E polynomial is that counting function, is the counting polynomial. So what Sam and I did, just using linear algebra in finite fields, is we just cut at least the orbit space, cut it up by orbit type, and then figured out how to count the number of points. And then we identified which of the strata were not going to correspond to GIT points and threw those out. And then we further figured out how to identify certain points that would be identified in the algebraic closure of the finite field, and had to take a quotient of certain strata. And at the end of the day, we had the counting polynomial for the GIT quotient. And then by this theorem of Katz, it's the E polynomial, which was kind of nice. So, this is an example of some work you can do with an undergraduate that doesn't use a lot of technology, but that actually has, so I think some interesting consequences. And then if you take the limit as q goes to 1, you get the classical Euler characteristic. I like to think of it as the number of points over a finite field of order 1, F1, because you're letting q be 1. But that's sort of, maybe a lie. You get the Euler characteristic. But nevertheless, I think there's a way to. I think it's maybe using multi-valued fields or something. Maybe there's a way to actually make that make sense. But anyway, but this is kind of nice. This wasn't. But you get this from. You can still get this from Tom's computation of the Poincare polynomial, though, gives this Euler characteristic too, so this is not really a new result. However, Vicente Munoz and I, using fibration techniques and not finite field techniques, not arithmetic techniques, did the SL3 case. And as far as I know, the Euler characteristic there is a new result. Okay. So that's just a little side note. So back to homotopy, which was asked earlier. So let this be the connected component of the trivial representation. So there's a fairly recent theorem of Indranil, Dan, and myself, which I really like to point out to, to the Higgs group. Because, one complaint I get from the Higgs group is that free groups are never Caylor. It's never, so why in the hell would they care about free group character varieties? But the point is that free groups sometimes sit in natural families of finally generated groups that also include Caylor groups. And sometimes the results concerning free groups actually do carry over to the whole family, like in this case. So this result was first just done for free groups by me and Indranil, but then Dan joined the party and we were able to do much more. But the bottom line is here, if you're dealing gamma as a free group or free Abelian group or the fundamental group of a closed ornamental surface, then the fundamental group of the moduli space has exactly the same form in all three cases. And there it is. So you look at the, so R here is, it's R as stated there. You look at the Abelianization of gamma, R is the rank, and then you just get pi 1 of G mod, the derived subgroup, to the rth power. In particular, G semi-simple is simply connected, which is, I find it a little bit surprising, actually, because there could be torsion in that case, and you might think that the torsion contributes to some homotopy. It certainly does on the Hom level. Like in the free group case, right, if you have like a not simply connected semi-simple group, the Hom space is not simply connected because it's just a product of G's. So why in the world does it become simply connected when you quotient? So somehow the singularities are killing the homotopy upstairs. And we conjecture this is more general. In fact, we think the general property here is that the relations in gamma all become trivial upon Abelianization. And that's what we think is actually going on, but we can't prove it. At least not now. Okay. Okay, so that's pi 1. Right? So what about higher homotopy groups? What about pi 2? Another result, this date actually shouldn't be, this was when I think we finished it, but I think it's been accepted, but it hasn't appeared yet. So maybe I should write that as 2016, I don't know. But anyway, so in this case, we can't do it, although we think this result's true for any reductive group, G, we only can do it in these cases. But then we show the pi 2 is trivial. And then actually easier than that in the same paper. We showed that if you look at the stable points from a GIT point or the point of view, or the singular, the smooth points from a geometric point of view, or the irreducible locus from a representation theory point of view, they're all the same in this case, then there's actually Bott periodicity on that locus, which is really kind of cool. But this part is really easy to prove compared to this. This is actually really tough. The idea that why it should be true is simple enough. I mean, pi 2 of g is trivial, right? Just for any g, right? So if you looked at, so here's a real simple case of the pi 1 example, right? Suppose g is simply connected, right? Should I use 0 or 1? I'm going to use 0 to stay consistent here. Okay. Right. So suppose g is simply connected, right? So then in the free group case, you just have, right? You have a natural map, and one can show that this map has path lifting. Okay. It's not too hard to do that. Anyway, you use Kempness theory again. That's the way to do it. And you replace this guy as far as your topological considerations are concerned with a compact quotient. Okay, and then you use path lifting results in the compact setting, which have been known for a long time. Okay, so take a loop downstairs, right? Lift it. It separates. It's a path now, but the fiber's path connected, so you can connect it in the fiber, and there's pi 1 surjective. Since the upstairs space is simply connected, that shows the downstairs space is simply connected. So why not do the same thing for pi 2? Right? We have pi 2 trivial upstairs, so now we have to lift. Not just lift loops, we have to lift we have to lift spheres, right? So you lift a disk, right? Or lift a 2-sphere, and you get a disk upstairs, and what happens with the boundary? Well, the fiber is actually PG, which is not simply connected, so that's the first problem. But why in the world could you lift it to begin with? It's not a fibration. There's no path. There's path lifting in the pi 1 case, but not in. It's not a fibration. It's very far from a fibration, and this thing is super singular. Okay, it's generally not a manifold. I mean, there's like lots of problems, you know. So why can you even homotop off the singular locus, right, to even potentially lift it at all? But then if you get over that, then you still have the problem that the fiber is not going to be pi 1, trivial, which you would need if you want to try to replicate that result. But anyway, that's the intuition. That's why we thought this theorem was true. Okay, but to actually prove it is. Took a lot of work, a really close analysis of the singular locus and the local topology, and some other things. So I got, 4 minutes? So real quick sketch of the proof. Because of the deformation retraction theorem I mentioned before, you don't have to consider GL and GL and UN. Okay, you can just consider the compact case if you want. And the same thing with SL versus SU. But on the other hand, the difference between SU and U is just a torus, which pi 2 doesn't care about. Okay, so really you can reduce everything just considering SU, and then you can also make this assumption here, because the cases of R and N that don't meet this inequality, you can explicitly compute. In fact, I did earlier. Okay, and I showed you what the answers were there. So the next step to do is to get rid of R. Really, you want to reduce to R equals 2. So here, if R prime is less than R, you can just include. So say you have like R tuples of matrices, like say you have 2 tuples, and they're irreducible. So there's no, in the GL case, there's no common eigenvector, right? You can just put an identity factor in the next one and get it into get a representation from the free group of rank 3. It's still irreducible because there was no common vector for the first 2, so there's not going to be a common eigenvector for the triple. Okay, so you get a natural inclusion here, and then this is just. Not inclusion, sorry. You get a natural map here. That's all. Right now, it's actually an isomorphism upstairs. But anyway, but you get a map. And then the inclusion of the irreducible locus into the whole moduli space gives you a map this way. And then, and then the same map that was up, that induced this morphism gives you a morphism down here. So you get a commutative diagram. Okay, and then the top map, it turns out, is an isomorphism by transversality. And you might be asking, can I use transversality to begin with? And the answer is definitely not. There's no, because these things aren't manifolds. Again, the quotient spaces are highly singular, and codimension alone does not allow you to use transversality to homotope things off subcomplexes. But on the irreducible locus, you do have a fibration, and you get this on the irreducible locus, and you get this map here. This right here should be, I mean, it's written correctly, but the point is that this should be Hom, the irreducible homomorphisms. But the point is, in that case, you can use transversality on the Hom level because Hom's a manifold, and then now the irreducible locus is high codimension, and the irreducible locus is open subset, so it's a submanifold, and then you can use transversality to show that the pi2 of the irreducible homomorphisms is the same as pi2 of all the homomorphisms, which then is just a product. And so this part's trivial there, and then this gives you an isomorphism between this and this, but it was independent of R. So then that you can use a little triangle here to show that's an isomorphism. Okay, and then the vertical maps, that's where all the money is. That is, they're surjective. And that's because you can show that this is two connected. But that's really tough. And that's where all the local topology comes into. Loosely, this follows from a much more general statement that we prove in the appendix of the paper, because it's just, you don't want to read it before you read the proofs of the main things. It's highly technical. But anyway, but the basic idea is locally, so the irreducible locus is dense. Locally, you can find neighborhoods that do where the reducible locus doesn't separate them. And not only that, they're simply connected. And so those local topological conditions allow you to prove that this is a two-connected map. And you can, it's not, this result has absolutely nothing to do with these moduli spaces. Under these conditions, you have a complex inside another complex, and you look at the complement of that complex, the inclusion map will be two connected. So it's a very general result under these conditions. Well, these conditions in quotes, they're a little bit more to it. But anyway. Okay, so once you have that, the diagram that was here allows you to conclude that there's an isomorphism, which then allows you to reduce to the r equals 2 and n greater than or equal to 3 case. In fact, you could actually do n greater than or equal to 4, because we've already shown that r equals 2, n is 3 is an 8 sphere, and so pi2 is trivial. But anyway, so then the last step though in r is 2 is you show that the r equals 2 case factors through the r equals 1 case, and just like I had that sort of triangle at the beginning was the exponential of the Weyl alcove. Generally speaking, this is always going to be a ball, and hence the r equals 1 case will always be contractible. So it factors through something contractible, so pi2 is trivial. And the reason you can get this part is actually kind of cool. The Hom space itself is a product of G's, and so it actually has a group structure. Now, when you quotient you look at the quotient, you lose the group structure, right? But somehow there's some minor memory of the group structure. So on the moduli space, there's actually some kind of memory of the group structure upstairs, and that memory is what we use to construct the diagram that allows you to factor the r equals 2 case through the r equals 1 case. Okay, anyway, so that's the theorem. And just a slight remark, in the pi1 case, I mentioned that the result was uniform across all groups that includes closed surface groups, free groups, and Abelian groups. The pi2 result I just shared with you does not generalize across those families of groups. In particular, you can I 3D printed the free group of rank 2 with SU2 as a solid ball. The Abelian locus inside that is the boundary, and so that's a 2-sphere. And so, in particular, that gives you an example both of a closed surface group and an Abelian group where pi2 is not trivial. But using stable homotopy theory, you can actually say more. You can show that for every genus, there is some n where pi2 of the closed surface group will not be 0. And what do I mean by stable homotopy? I mean like embed SUN into SUN plus 1 and look at like a direct limit of moduli spaces in that way. And then you can determine what the topology of that direct limit is, and then you can use that to get this little result here. Okay, so that's the end of my talk. Thank you, Bill. As I said yesterday, you're an inspiration.
Comments, questions?
I got a question. Am I allowed to drink this?
Yes.
Yeah, okay.
It's, I brought it from Flint. Stopped by on the way to the airport.
Yeah, I appreciate that. It's good. So, lead.
Okay, let's thank Sean again tonight.